So I think we can start. Yeah.
Yeah.
Right? Everyone can hear me and see.
Yeah. Do you want to check first? Yes.
Just give me 1 second. I will just share my screen.
So I think we can start.
Yeah, just give me 1 second.
Yeah, we can begin now. You want to introduce him?
Yes. Yeah, he wants to check his screen.
Yeah. Little bit. My screen has a little bit issue. That's why I'm a little slow. So sorry for that.
Seems somebody's speakers are still on.
I will full screen. Yes.
Yes.
Can.
Yes. We can see.
Yeah. Everyone. Yeah. Oops. Sorry. So yeah. Let me know when I can start.
Sure. Good evening, everyone. Welcome again to the Special Functions and Number Theory Seminar. Our speaker for today is Dr. Shashank Chorge from IIT Gandhinagar, and he will be talking on Voronoi summation formulas, sign changes in these type sums, and Cohen type identities. Thank you, Shashank.
Yeah. Thank you for giving me this opportunity to present. So today's talk is going to be on Voronoi summation formulas and Cohen type identities. And this is the work that I did. This is a joint work with Dr. Atul Dikshit. So to begin with, first I will go through as the tradition goes. I will go through some basic ideas. Most probably everyone is aware about those things, but I will go through and then I will start introducing the definitions and the results, etc. So yeah. So first we define divisor function, which is straightforward, the sum of divisors of number n, and Lewis lambda function, which is -1 raised to total number of prime factors of a number. So, and if a number is does not have multiple prime factors, then mu of n, which is Mobius function, is defined as -1 raised to total number of prime factors. And if it has prime factor repeated, then it's equal to 0. The reason I am defining these three functions out of all the arithmetic functions, because our results are related to these three functions. Mostly we worked on these three functions. Now we move on to one of the most important functions in number theory, that is Riemann zeta function. The basic definition of Riemann zeta function is as given. It is sum of n raised to minus s for real part of s greater than 1. And we can always extend it throughout complex plane with a simple pole at s equal to 1. And the following is the functional equation of Riemann zeta function. Now, of course, there are many functional equations available for Riemann zeta function, but the reason I chose this because this function, this representation, or this asymmetric functional equation plays important role in our theorem. This is more for deriving Voronoi type summation formula. And chi of s is defined as quotient of gamma functions. Moving on. So what are Voronoi type summation formula? So if I want to define what exactly Voronoi type summation formula mean, basically they are the summation formulas for arithmetic functions derived using functional equation of Riemann zeta function. That kind of definition we can give. So of course, out of different functional equation, the one which I mentioned before plays a critical role in the derivation of Voronoi type summation formula. But of course, the further question is why we are interested in these type of summation formulas. And for arithmetic function, whether it's a divisor function or Mobius function or Liouville function or whatever function we can think of, there are generally formulas available with certain error term and so on. So why we are deriving a new summation formula, and what's the special thing about it? So first, let me show what summation, Voronoi summation formula looks like, and then I will explain the importance as well. So for a divisor function, the Voronoi type summation formula is as given. We can see that x log x here is the main term. So I'm using my writing pad. I hope it works. Just give me one. Yeah. So can everyone see? Can I do annotation?
Yes.
Yeah. So this is the main term, and if we have seen Dirichlet divisor formula, Dirichlet's formula for divisor function and all, we can see that this is the exactly same main term we get. But now the rest of the thing becomes slightly complicated. We can see that it is not very simple. Y sub nu is a Basel function of the second kind, and K sub nu is a modified Basel function of the second kind, right? So it's not like it is not as simple as the formula which was given by Dirichlet. So uh, why it is so important? So yeah, so, oops, I think I need to clear this just. Yeah. So, Dirichlet divisor formula, if I have to represent, I mean, if I have to give the statement, we can see that the sum of divisors up to x is given by x log x, which is the main term, 2 gamma minus 1x, and then there is error term delta x. That delta x was initially by Dirichlet himself was approximated to be x raised to half. This was x raised to half by Dirichlet's hyperbola method, but it is conjectured to be x raised to 1/4. So is there any way to improve this error term? So improving this error term was extremely difficult till Voronoi gave its sorry till Voronoi gave its summation formula, and using that summation formula, he proved that the error term can be reduced to x raised to 1/3 log x as x goes to infinity. Of course, the conjecture is still open. It hasn't been settled because it is still far from x to the power 1/4. But after Voronoi's improvement, which was 100 years ago, there have been further improvements as well, and most of them used uh, Voronoi type summation formula. So there have been, so 1/3 is not the best bound, I guess. Now there have been small improvements, and slightly like 0.31, I guess, is the current estimate, the best available estimate. So now Voronoi decided to generalize it. So he added a test function f of n, and then the formula became this with added function. So we don't have to work with just d of n, but we can have test function and we find weighted sums. And we can see that in the yellow part, this thing is called as the kernel of the Voronoi summation formula. This plays very important role because this estimating this kernel basically gives us the better bound in error terms and so on. And f of t is a function with bounded variation. So there are some weak restrictions on f of t. Now, if we generalize further with respect to divisor function, then we get this formula. We can see that as we generalize more and more, the formulas are becoming more and more complicated. So this is the main term, and the kernel has again become slightly complicated. We can see the yellow thing represents kernel. Now, it is very natural that in any case, can we generalize these type of summation formulas to other Voronoi type summation formulas to other arithmetic functions? And if we can do that, maybe there is a chance that we can improve the error bounds for those functions. Because a lot of times estimating the error bounds in the summation of arithmetic function. These are very famous problems. We can take any arithmetic function, whether it's Liouville lambda, Mobius, or square of divisor function or anything. Mathematicians are generally interested in bounding the error terms. So why can't we just generalize these formulas for other arithmetic functions and then see if that is possible? So of course, the first step, what we have addressed is generalization. We haven't addressed the part of approximating the error term because it's completely different project. So we might take that project in future. But generalizing the sums for other arithmetic function itself is quite interesting task. So again, we come to certain definitions. Now we are going into the results that we derived. So d square n, which is square of divisor function, uh, not convolution, because certain, I think such results are available for convolution. So we go with regular multiple. Sorry, I can't hear. Hello.
I think you can proceed. It was just somebody's speaker on.
Okay. So d square n, is square of divisor function, is has a Dirichlet series representation given by the following formula for real part of s greater than 1, and of course it has a zeta closed representation in terms of zeta functions, which is zeta raised to 4s divided by zeta 2s. So this raised to 4 means just a regular fourth power. This doesn't mean composition and all. Just avoid confusion. So yeah. Now before we this, so there are certain, what we are going to do. We are going to have a, just like the previous case, we had a sample function. We are going to work with certain sample function with respect to certain restriction. So first, let me state the result, and then I will elaborate on that result. So first, let's set up some hypothesis. Let phi of x be a holomorphic function in the strip -1 to 2. So this is a vertical strip, and phi of s has a certain decay rate. So we need this restriction as t goes to infinity in the strip. So it's a holomorphic function with respect to this decay rate. Then in that case, we have, oops, we can define its inverse Mellin transform as a small phi of x, as this thing, inverse Mellin transform of this function. And just let me clear this. In that case, we get a Voronoi summation formula for d square as follows. So d square n phi of n summation n 1 to infinity. This first integral kind of represents main term. So saying main term and error term is not quite right in this case because we don't have any error bound or big O term. But if we draw the analogy from previous results, we can say that the first term is kind of main term, this thing. And interestingly, we get a series of zeta zeros. We get a infinite series of zeta zeros, which was not the case in the previous results. And this zeta zero series appears because of the representation of d square n. D square n has one zeta in the denominator, and that is why it. And now the kernel has become even more trickier. So the kernel is like this. We can see that this part is kernel. Kernel is slightly trickier than the previous cases. So as I mentioned, as the complexity of a function, arithmetic function increases, so d square's representation is probably more complex than the other functions we considered. So that's why the kernel also becomes a little more complicated. So, oops, yeah, sorry. So most of the things are well defined here. I mean, K is Basel K function, Y is Basel Y function, and A naught, A1, A2, A3 are the explicit constants, which are basically can be found out in terms of zeta and gamma functions. So the only thing here that is little less known is B of n. So where this B of n appears, we did not talk about B of n. So B of n is nothing but we can see that the coefficients of the Dirichlet series of zeta raised to 4s divided by zeta raised to 2, zeta 2s minus. So the coefficient of this series is nothing but B of n. And of course, we can find explicit representation for B of n as well. B of n is a completely multiplicative function. So only we need representation for prime powers. And for prime power, the representation is given as follows: k plus 3 choose 3. This is a combinatoric symbol, minus p times k plus 1 choose 3. So of course, when k plus 1 is smaller than 3, this becomes 0. And that is the representation for this. Now, okay, let me go back for a second actually. What is the interesting thing about this representation of this Voronoi summation formula when we generalize what is it? So let me even go back further. So I'm going back to previous slide, and we can see this result for divisor function. This is the Voronoi summation formula for divisor function, and the yellow part represents the kernel, right?
Shashank, for some reason, your yellow is blue here. So I guess that's because of your screen.
Oh, sorry. I'm really sorry. Actually, my screen is not showing colors or showing different colors. So I'm what I see, I say. But yeah, it could be blue. I'm really sorry for that. Okay. Okay. So yeah, I will say this. Okay. So yeah. So the same kernel has been multiplied here. We can see that the exact same kernel has multiplied here. We see two identical copies of the kernel, and there is of course some additional part as well, which is cosine. But it is quite interesting that as the power of divisor function increased, it became square. We got two copies of the kernel, and of course even more interesting is that we got series of zeta zeros, which is this. So yeah. Okay. Now yep. Okay. Now there is something called as Cohen type identity. So initially we talked about Voronoi type identity, Voronoi summation, which I just showed. Now I'm showing a different identity called as Cohen type identity, or sometimes called as Voronoi Cohen type identity. And why we are interested, why the identity is interesting. So I will explain that as well. So Voronoi and Cohen discovered this identity. I guess that is in blue, that shows in yellow in my on my screen, but this is the identity which they derived. And if we put if we replace x by ix in the original identity, and x by minus ix, and then add and simplify, I mean basically some elementary algebraic operations, that's it, we get the following identity at the bottom of the page. Now, if you look at this identity is interesting because on the left-hand side, we have an infinite series such that its residues at the complex natural numbers is nothing but d of n. Suppose I take a contour. Let me just suppose I take a contour around positive imaginary axis and find the residue at these numbers. These residues are nothing but d of n. So if I integrate around a contour, if I integrate this function around a contour, I will get Voronoi type summation formula, which was Voronoi type summation formula for d of n. And this method is called as Koshlikov's method for finding Voronoi summation method. So, and of course, the original formula derived by Voronoi was, the method was much more complicated, and Koshlikov uh, simplified, provided that the sample function uh, f of t that we multiply, sorry, f of n, d of n, f of n, there is a sample function. If this function is holomorphic, if f of n is holomorphic, then Koshlikov's method works. And this is much, much simpler than what Voronoi used in his case. So this method, uh, then of course, there was a natural question. Can we use this method for d square? Can we use the same method for d square and find the Voronoi summation formula for d square? But unfortunately, the answer is no. We had to use a different method to find Voronoi summation formula for d square. This method does not work, and the reason is, just let me go further. Yeah. Yeah. So first I will show what the formula looks like, and then I will tell you why the thing doesn't work in our case. So the same idea if we use for the d square, the uh, Cohen-Voronoi type identity kind of looks like this. Okay, where again k is Basel k function, and uh, uh, these are residues of zeta function and gamma, whatever residues we encounter. I mean, they have explicit representation in the following slide. Okay, but the problem appears because of this type of series. As we can see, just let me go back for a second. We can see that this is an infinite series of residues. The last part of the slide, we can see that is an infinite series of the residues involving zeta zeros, and this looks like this. That series looks like this. Okay. The other residues are pretty simple. They do not cause any problem because they are finite in number. But this series is infinite series. These are infinite series of residues that we get. And if we try to apply, I'm not going into too much technicalities because that will take a lot of time. But the problem that we encountered was like series, this series infinite. Oh, sorry, this infinite series that we are seeing here. We do not know in how much, how can we extend it to, analytically extend it to larger region, and that was the problem we encountered, and that's pretty tricky because not much known about values of the derivatives of zeta zeros. Values of the derivative of zeta function at the zeta zeros. So I mean to say, this zeta prime rho m, there is not much known about these type of values. So extending it to higher region was very, very hard, and that's why we had to go by a different approach, and eventually we found summation formula for that. Okay. Now the question is again, of course, if the Cohen type identity can be found for divisor function, then can we generalize it to even sorry, square of divisor function? Then can we generalize it to the product of divisor function, generalized product sigma a sigma b? And of course, yes. And the Cohen type identity is this. Again, it's not a Voronoi summation formula. Voronoi summation formula for sigma a sigma b, even though we did not find out, it is possible, it's not very hard, but it is very clumsy compared to the formulas we have found out, which look kind of neat. If we try to find Voronoi summation formula for this function, which is sigma a sigma b, it is going to be little clumsy. So we decided not to go into that. But the Cohen type formula, which I mentioned just now, is kind of elegant, and it looks like this. Again, k a k b minus 1, these are Basel k functions, and these are what we are saying at the bottom of the screen in terms of R are nothing but residues of zeta function. Residues occurring due to either zeta or gamma function. But again, uh, uh, oops, yeah. Again, if we see this part, x raised to minus a minus n raised to minus a, x raised to minus b minus n raised to minus b divided by x square minus n square. Look at this expression. And let me go back for a second and this thing. Oops. We, here, this time. Yeah. That part is very similar to what we are getting here, right? If we have extra parameters a and b, if we take the limit a and b go to 0, we get this, right? And this formula, which we derived in our paper, is very similar to what Voronoi derived or Cohen derived in his paper. Now, if we do comparison, here we have x log x divided by n, right? And in our case, we just have one extra power of log, that is log square x divided by n, and everything else remains the same on the left hand side. And then, because of all these things, it's very difficult to directly apply Koshliakov's approach, which I mentioned, like the contour and all those things, because of all these things. The formula changes slightly, and then we have infinite series of roots and all, etc. Okay, now let's go to Liouville lambda function. Liouville lambda function, we also derived similar identities for Liouville lambda function. Liouville lambda function has the following representation, which is zeta 2s divided by zeta s for real part of s greater than 1. Similarly, now we go with the hypothesis phi of s. Phi of s be a holomorphic function in the strip, but here we are having a weaker restriction that phi of s can have a pole of order 2 or less at s equal to 0. In the previous hypothesis, phi of s was completely holomorphic in the strip. Here, we are letting it to have a pole because a lot of Schwarz type functions and a lot of Ries type functions have a pole at s equal to 0. And we wanted to include those functions in our formula. And that's why we reduced the restrictions on P of s. So just wanted to point it out. Of course, and phi of s again has a certain decay, which is given by the -1 raised to minus delta. So in that case, the Liouville lambda function, we have the following Voronoi type summation formula. So this is kind of main term. Okay. This is infinite series of zeta zeros. Okay. And this is kernel, the last one. Okay. Again, we can see that as the representation of lambda is simpler compared to the representation of d square, the kernel is also very simple. Kernel is nothing but the sine function divided by root x. That's it, this part. And Cn is a multiplicative function given by p times mu of q, where n is p square q and q is square free. So that is the representation for C of n. Okay. Now, oops.
Okay, sure.
Okay. Okay. Now, what happens in our case, as I mentioned, that we have to just let me go back again. I'm just going back and forward so that we don't lose touch with So phi of s is a function, and this function here is inverse Mellin transform of that phi of x. So I'm just repeating this thing. So this small phi of x is nothing but inverse Mellin transform of large phi. Okay, so this is the function on which we put restrictions, but in the formula, this is the function that we use. So this goes here. Okay, so yeah, and as I mentioned, this function has possibly at most two poles. I mean, pole of order 2 at s equal to 0, and the reason was like we wanted to include Schwarz type function and Riesz type function. Okay, so now the things become little tricky if we let this function have a pole, then deriving Voronoi type summation formula becomes slightly tricky, and but we eventually overcame that part with respect to something else which I will explain further. So let me, yeah. Okay, so before that, as I mentioned, what C of n, we just saw the definition of C of n. C of n has a Dirichlet series zeta 2s minus 1 divided by zeta s. That is the Dirichlet series representation for C of n. Now, Vinogradov-Korbov, if we use the Vinogradov-Korbov zero-free region, we get the following estimate for the sum C of n divided by n, which is equal to half. C of n divided by n equal to half. I mean, it is not hard to see that if we take this limit s goes to 1, basically we get the same thing, right? Limit s goes to 1. If we use power series representation and all, but of course taking inside the limit is not easy, inside the sum is not easy, because this is not absolutely convergent, right? Not absolutely convergent. So we can't just not absolutely convergent and so on. So we can't really take this, we can't use any of the DCT or MCT or any convergence formulas. So we go by the traditional approach. We use Vinogradov-Korbov zero-free region and then do contour integration to get this formula. Okay. Now, why I'm talking suddenly about this formula when we were talking about identities, and the reason is these estimates were extremely important for us. There is one more estimate actually. Cn log n divided by n is minus gamma over 2, and it was done using the same method, Vinogradov-Korbov zero-free region and contour integration. Because without these estimates, we could not derive the summation formula with for when this sorry when with sorry as I mentioned this bs, this was this, right? So this function had a pole, right? So without that computation which I mentioned, C of n divided by n and all, we can't really derive the Voronoi summation formula without that. So when the poles appear, things become complicated. So we need such type of estimates to generalize for functions having poles and all. So which makes things even more interesting. And the reason why we did not use these type of function in the previous case, you might have observed that we did not have such estimates or no mention of Vinogradov-Korbov zero-free region and so on. So the reason was it is doable, but it again becomes too complex and too cumbersome. So I should use the word cumbersome rather than complex. So that's why we decided not to uh, not to introduce pole in the previous when we dealt with d square n. But when we deal with lambda, introducing pole, this can be handled. This can be handled with by uh, finding these type of estimates. Okay. Now, of course, what we did is like finding certain identities. So a lot of Rees type and Schwarz type functions, if we use them as sample functions, what identities we get. So we derived a lot of I'm not giving all the identities. Some of the interesting looking identities I'm giving here. So we can see that there is an exponential decay on the left hand side, and there is this function on the right hand side. Then yeah, for lambda, if we use exponential decay, that is e to the power minus ny, then we get a nice function like this. And this is explicit evaluation, by the way. And further, if we assume Riemann hypothesis and absolute convergence of this series, which is involving zeta zeros, then we can say that as y goes to 0, we get this type of bound as well. So this summation is nothing but big of 1 over root y as y goes to 0. And yeah, and if we use Schwarz type function like this, oh sorry, Rees type function, not Schwarz, Rees type function like this, then we get another identity. So in the paper, we even derived even more identities, but I did not want to include all because it will be just a series of identities. So it will be better to just show some of the interesting looking identities. Yeah, and again the same thing. If as here y goes to infinity, in the previous case it was y going to 0. So as y goes to infinity, we get this summation as big of root y. Okay, and again we do the same thing with the Mobius function, which we did with the Liouville lambda and d square, and we get this formula. This is the last part is the kernel. You can see that there is a infinite series involving zeta zeros, which is the first part, and this thing. Now, going ahead, we talked about identities and all. Now, there are certain approximation which we did for Rees type sums. So I'm going to the next part of the paper, which is Rees approximation of Rees type weighted sums of arithmetic functions. So I will explain everything, but first I will read the theorem's statement. Assuming Riemann hypothesis and Gonak-Hedgehal conjecture and simplicity of non-trivial zeros of the zeta function, for any m greater than 0, however large, we can take sufficiently small delta depending on m such that lim sup of this function is greater than m and lim inf of this function is less than minus m. Okay, so this is a weighted sum. Delta is always greater than 0. If we could hypothetically, even though we can't make, but if we could make delta equal to 0, we can see that the results we get are very similar to the conjectures for sum of mu n. Okay, but in this case, of course, we can't make delta equal to 0. Now, Riemann hypothesis is well accepted, and everyone knows Riemann hypothesis is nothing but root of all the zeros of all the non-trivial zeros of the zeta function have real part equal to half. And simplicity of non-trivial zero is also kind of well known, right? Roots don't repeat themselves, right? All each
for the linear independence conjecture.
Yeah. And there is one more conjecture, which is linear independence conjecture, which I did not mention here, but we need that. So linear independence conjecture says that suppose gamma 1, gamma 2, these are the imaginary parts of non-trivial zeros. Positive imaginary parts, of course, imaginary parts greater than 0. Positive imaginary parts of non-trivial zeta zeros, then they are linearly independent over rational numbers. these are linearly independent over rational numbers. Okay, that is linear independence conjecture. Even though it's conjecture, it is well known and well accepted to be true since more than 100 years, and a lot of interesting results have been derived using linear independence conjecture. So yes, in our proof we also use linear independence, and even though it did not mention, it does there is linear independence conjecture here. So using these we can derive these. So okay, most of the things I cleared except what is Gonak-Hejhal conjecture. So Gonak-Hejhal conjecture is something I did not mention because the rest of the conjectures are pretty well known, whether it's RH, simplicity, or even linear independence, they are well known and well accepted. But what is Gonak-Hejhal conjecture? So this conjecture states that summation 1 over absolute value of, oops, so, give me one sec. Yeah, absolute value of zeta prime raised to 2k, okay, where gamma m, which is the imaginary part of the zeta 0, is less than equal to t, absolute value less than equal to t, is bounded above and below by t raised to log t raised to k minus 1 the wholes, okay, for k greater than 0. So this is Gonak-Hejhal conjecture, okay, for all k greater than 0, sum up to t of the derivative of zeta function evaluated at zeta zeros raised to power 2k is given by this. Okay. In our case, we need uh, sorry. In our case, we need k equal to just half. Okay, k equal to half, then this becomes the power becomes 1. That's the only thing we need. We don't even need the whole conjecture. But interesting thing is that the lower part of the conjecture, the lower bound has been already been proved. So less than equal to t raised to 2k is greater than t log t raised to k minus 1 the wholes. So this has been proved. Okay. Upper bound has not been proved. Upper bound is little tricky to prove. So that is why we had to assume conjecture. But for lower bound, we don't need to assume anything. This is just using Riemann hypothesis and simplicity, etc. This has been proved. Okay. So using these things, we get very interesting estimates for the weighted sums of Mobius function, weighted Rees type sums of Mobius function. Okay, and similar ideas we can use. Similar type of ideas we can use uh, for other functions. Oops. Okay, I think I had the explanation, but we may not have a lot of time to go through. So I will just go. I will not go through explanation because we are actually probably running out of time. So for lambda also, we have similar type of bounds. Lim sup is greater than equal to m. Again, the Rees type sum, exactly identical to mu of n. This thing, and the lim sup is lim inf is less than equal to minus m under identical conjectures. And for d square also we have similar results. D square results are slightly complicated. D square we can see here it is not just any delta greater than 0, but rather 1 plus delta, right? And g of y is a polynomial given in the bottom, polynomial in log y, multiplied by y. So this is the function g of y, and this is the bound we get for d square and divided by y raised to 1/4 and so on. Okay. So yeah, I mean, the ideal case would be if we could really put delta equal to 0, we could get a lot of conjectured bounds and all. But of course, because of the limitations, we can't put delta equal to 0 because of we don't have results for such things. But yeah, and the last part is okay. So what are the further problems we can think about? Further, what are the further scope of this project? So Voronite summation formula, how can we use that formula for reducing the error term of d square n less than equal to x d square n? So that will be kind of a good project, good challenge, because the error term. So let me explain the error for d square n. The error term, I think the current known is x to the current known error term is big of x to the power half unconditionally, but it is conjectured that again it is similar to the divisor function. It is conjectured that this should be this should sorry, let me just if this is known, the error term for d square is big of x raised to half, and it is also known that this is omega x raised to 1. So these things are known, these are proved. So the conjecture is delta x is big of x to the power 1/4. So that is the conjecture. It is very similar to the conjecture for d divisor function, Hardy's conjecture. So it will be interesting if we can really reduce x raised to half any further and bring it close to x raised to 1/4. Even if we can't really achieve the optimum result, at least it should be possible to reduce the bound. It will be interesting to see that. And the other part, which is slightly less difficult, I believe, is that how can we use Cohen type formulas to derive Voronoi summation formula, which I mentioned earlier that we had an infinite series of zeta zeros, which was the problem in our case. In our case, the Cohen type formula was had a infinite series of zeta zeros, and that is the reason we can't use the technique, that Cohen type technique. So, is there any way to bypass that problem? Is there any way to, analytically continue that series and so on? So, these are the two problems will be very interesting to explore in future. And yeah, that's it. So thank you for inviting me, and if you have any questions, please let me know.
Thanks, Shashank. Are there any questions for Shashank?
Hi, Shashank. This is Vivekananda.
Hi.
So it was a very nice talk.
Yeah,
Okay.
thanks.
Yeah. So I just like few comments. Like at the end, you said that like error term for this d square end, like summation formula. You mean like conjecture is big O of x to the power 1/4 plus some epsilon is required because.
I don't
Because already omega of x to the power 1/4 has been done by Chandrasekharan and Narasimhan. Because without epsilon.
No, I think without epsilon also is possible. It is possible because it's just it should be possible. I mean that's the conjecture, I guess. Yeah. We don't need that epsilon because what you said is right. Yes, it has been done, but that is just omega, right? I mean, so yeah, it should be possible because it shows that the thing divided by x raised to 1/4, this Let me show. Yeah. So basically, what it is shown is n less than equal to x d square n divided by x raised to 1/4. This lim sup as x goes to infinity. This is just greater than 0. That is basically omega bound. So yeah, so there shouldn't be any problem to get x raised to 1/4 as a conjecture.
Okay. Mhm.
So
Okay. Yeah.
the current best bound is due to GI and Shankar Narayanan.
Mhm.
It's big O of x to the 1/2 log x to the power 5.
That is unconditional or
Yes.
conditional.
That
X
is
raised to yeah log x. Yeah, yeah. Sorry, I think that log x part.
log x to the power 5. Yeah.
Log x, that is unconditional, I guess, and with RH I guess we get x raised to half, something like that. I
Yes.
maybe yeah, yeah.
And these Voronoi summation formula for d square n, first it was given by, I hope, Ramanujan, like in his he didn't give a proof, I think, in his paper.
So there wasn't a Voronoi summation formula.
Like
No, I think
yeah,
Voronoi was not there. He had
like
that
main term and error term he
Yeah.
gave.
yeah, yeah, yeah.
Asymptotic
That's
formula was there.
Yeah.
yeah, yeah. But Voronoi was not there. Of course, he gave asymptotics and he gave some conjectures. I guess three fifth or something. I guess he had.
Yeah.
Ramanujan
As
had.
far
Yeah,
I remember, error term he gave 3/5 plus epsilon.
Yeah.
yeah, right. So, but
So
Voronoi was I guess this.
yeah, so yeah, and one more thing, like in the same paper, he actually not only for d square n, like he mentioned for any higher power of dn also. Yeah,
Okay.
like as far I remember.
Mhm.
So maybe it might be also like a good to think like whether Voronoi type summation formula for higher power of d of n can be, I
Yeah,
think.
actually, I guess we had discussed it. I and Atul sir discussed that higher power thing as well at one point. But
Mhm.
I think the zeta representation was slightly
Yeah,
more complicated. I mean, for d square, it is still
yeah.
complicated, but not that much can be handled. But
Mhm.
as we go to 3 and all, it became really, we thought it would become much more clumsy. So, yeah,
Yeah.
yeah. But yeah, if someone wants to try, that is always.
Yeah.
Okay, thank you. Yeah.
Yeah, yeah, thanks.
Any other questions? Okay. If not, let's thanks Shashank again.
Yeah,
Thank you.
thanks. Yeah.